Anyway, we have a new slot now. Henning Paul from Bremen is going to present something very, very interesting. He has grabbed some, Henning, he's there. Yeah, hello, welcome, Henning.
Bin gleich live in der Konferenz.
Hello. So, Henning is sitting in the sunshine. That's a nice place to sit. Henning was retrieving some Bitcoin mining controllers and was doing very funny things about them, using them for SDR. Please give Henning a warm applause. Okay, since this is also a remote talk, we've pre-recorded it. And please think about your questions during the talk and raise them afterwards.
So, hello, and thank you for the kind introduction. My name is Henning. Maybe some of you know me from last year. Last year, I held a talk on a homebrew receive SDR, and this year, I will present to you the transmit counterpart to this thing that I presented last year. In the meantime, I have received my ham radio license, so I'm finally able to transmit legally. So this is why I put some effort in designing transmit capable software-defined radio. Okay, so let's start with the slides. What I will show you today is structured as follows. It will be just 19 slides. I will start with a quick recap on what you saw last year, and then I will go over to how the hardware of my new design looks like and how the corresponding software looks. So let's go. The recap. On last year's SDR Academy, I presented a receive SDR, which was based on a Xilinx Zynq evaluation board, for which I designed an add-on board with a high-speed analog to digital converter, 40 megasamples, 12 bits. And I also showed you some of the add-on boards that I built in order to receive VHF and UHF signals. But for shortwave itself, you can directly use this ADC board. And due to the fact that it has two ADCs or a two-channel ADC, in direct sampling mode, you can simultaneously digitize two receive signals in order to, and therefore exploit some MIMO technologies, multiple antenna stuff, and pull some gains from that. This is what I presented last year with an example reception of a continuous wave signal in the 40-meter band. So that was where we left off last year, and now I would like to go on to what I've did in the meantime, the last 12 months. So I received my amateur radio licenses, first the novice one and then the full license, and therefore I was finally able to transmit on the corresponding ham radio bands, and so I decided to build a transmitter SDR. And approximately at the same time I was studying for my license examination last year, I ran across an article at Hacker Day where they presented a very cheap Xilinx Zynq FPGA board with exactly the same processor that I used on my that's used on the evaluation board on my receive SDR, and so I got interested in this topic, and I just ordered a board for 15 euros, which is significantly cheaper than the say cheapest evaluation board you can get from on this Xilinx platform, which is 160 euros. These Zynq boards are used Bitcoin mining controllers, so not the boards that mine the Bitcoins themselves, but the boards that do the interfacing to the Ethernet, and the boards that shove raw data into the mining boards and back. And these boards can be bought used for 15 euros last year. Now it's up to, I guess, 30 euros, but it's still significantly cheaper than a full evaluation board. So I checked if one can use these boards as a very inexpensive platform for software-defined radio. So the main difference to the, say, real evaluation boards is that these Bitcoin mining controllers only have 100 megabit Ethernet interface, in contrast to the gigabit interface that the usual FPGA evaluation boards have. So this proved to be a bit of a bottleneck later on, but I will show you how I came around this, say, restriction. So when I received this evaluation board, what I tried first was to get PetaLinux running. PetaLinux is the embedded Linux from Xilinx. It's based on Yocto Linux with some add-ons, modifications. I already used PetaLinux on my previous SDR, the Receive SDR. So I had some experience, which was actually very valuable, because when you have a board which is poorly documented, you need to know what you're doing, because you cannot, say, follow the tutorial step by step like you do it for the regular evaluation board. You have to know all the intricate details of PetaLinux, which are not that say user-friendly for someone who hasn't worked with this before. So it took some weeks to get this running, but finally I was able to boot PetaLinux 2020 on this 4205 board, and I also managed to get the 100 megabit PHY chip running, which was a bit tricky because it doesn't have the dedicated crystal that PHYs normally have. So you need to configure the FPGA to generate corresponding clock signal in order to get the PHY running. So this was a bit tricky, but I finally got it working. So I had, say, a plain vanilla PetaLinux running on this Bitcoin mining controller, and now I was able to do something more useful with this board. Something of the stuff that I originally planned to do. It means generating a signal in order to transmit. So what I did next was I took my a part of my older USB-based SDR that I built a few years ago in 2017, I guess it was. I also talked about that last year. And I hooked up the transmit part, so the DAC part of this board with a, say, flat cable to this Bitcoin mining controller, and also hooked up the I2C. And then I was able to plug together a block design that was able to play out samples received over Ethernet over this parallel bus into the DAC board. And after a few days, I had it running so far that I was able to generate already the first signals on 70 centimeters. I used an old modulator board that I designed in 2016 when I was back at the university as a researcher. Those of you who saw my last year's talk also know what I'm talking about. I hooked this up, and voila, I was able to generate a signal on 70 centimeters using this, say, mesh. Yeah, you see on this picture here, yeah, consisting of this Bitcoin board, the DAC board, and the modulator. And while I was at it, I was thinking, so we have this bottleneck of 100 megabits here. So means we cannot use the actually full 40 mega samples per second bandwidth of this DAC because that would require 80 megabytes per second. Of course, that won't work out. We need to put some logic into the FPGA. And one thing that I was doing first was I built an FM modulator in the FPGA. Means you only transmit the baseband signal, means either the audio signal or the modulation signal when you want to do FSK, for instance. basically it's just a few lines of VHDL. And here in the slides, you see basically it's just a lookup table with a sine wave. And then what you do is, yeah, like a DDS usually works, you just walk up and down this lookup table depending on your input value. And this is how you can easily generate an FM signal just by walking around this this lookup table. And it was just very few lines of the HDL code. But one important lesson that I learned was you definitely need some dithering, because if you don't do this, you get some nasty spurs in your spectrum. So it's important that you say add a random bit, a pseudo-random bit in the least significant bit in order to get a nicer FM signal without these nasty spurs. So that was one thing that I learned when I implemented this frequency hard modulator in VHDL and hardware. Yeah, that was one way to do it, but of course you don't always want to do FM. Of course, you also want to do other modulation schemes. So this is why we also needed, say, more generic mode. So this is why there's also an interpolator in this FPGA included in this block design that will just interpolate the input signal by a factor of 16. Means from 5 megasamples input, from 2.5 megasamples input, you can get 40 megasamples output. This has also one nice advantage also is that you can do, for shortwave transmission, this is essentially important, do a frequency up conversion in the digital domain. I will come to that in a moment. Before that, I would like to just show just a quick picture of a modulator that I quickly designed. It's basically just the from the evaluation board inspired. It's a modulator in order to do VHF, so means 2 meters, using this modulator board, because the other board that you shown before from this one from 2016 is only suitable for 70 centimeters and up. So for VHF, I needed this board here. This is also usable for 6 meters as well. This is what I'm currently working on. So for the VHF bands, you need this modulator. But what was particularly interesting was shortwave. This is why I introduced this digital up converter, which is basically very similar to the digital down converter that I showed you last year. It's just multiplication with a sine wave in the digital domain. And you can see here on the slides that it's basically just, again, a sine wave in 16 steps, quantized to integer. And then what you do is basically you only multiply the output signal, the interpolated output signal, by the values in this lookup table. And this is what you see here in the VHDL code. It's just really simple. It's just a pointer going through this lookup table, and the pointer increment tells you how much you upconvert. Yeah. So if you increment with every input sample the lookup table just by 1, you will then just upconvert to basically the input sampling rate, means 2.5 megasamples if you use the 40 megasamples output rate. And if you increase the pointer by 2 in every iteration, for every new input sample, you basically get a 5 megahertz intermediate frequency. So this is just very straightforward approach, but it works very, very well. Of course, this mixer only supports integer multiples of output rate by 16, means integer multiples of the input data rate. For any, say, the difference between your desired transmit frequency and this intermediate frequency, of course, you can do in software. In GNU Radio, you can just modulate it to an, say, intermediate frequency, and then do this hardware up converter to the rest. And this is how you can generate signals up to 15 meters, means 20 megahertz for 40 megahertz sampling rate. I was able to tweak the sample rate a bit higher. I will show you how on the next slide. What I did, basically, I made a new digital to analog converter board, which you can see here. This is the board that you directly attach to the GPIO connector of this Bitcoin miner controller. And you have basically then I and Q outputs here differentially, directly. This is a high-speed digital to analog converter of analog devices, 809707. Yeah, I guess that's it. It's the number. This one, I was able to achieve sampling rates of 60 megasamples in this case. On the, say that the DA converter is running at 60 megasamples per second, means the input rate on the Ethernet is 3.75 megasamples per second, which is actually the upper limit you can reliably transmit over 100 megabit Ethernet, because this would be 7 megabytes per second. And you don't want too many packet losses. So basically, this is the barrier that I found out that you should not exceed on the Ethernet interface. But it's not bad. It means I can work a lot of shortwave bands using the setup, and yeah, it works quite well actually. Of course, if I want to do actually do QSOs, I need an amplifier, because of course what comes out here is, say, 1 volt peak to peak. Yeah, means I need some amplifier in order to get some power into my antenna. This is why I designed this little board here. This is basically the amplifier part from the Hermes-Lite 2. So Hermes-Lite 2 uses keycut, so I can directly, say, copy the part of the schematic that corresponds to the amplifier, and then I made a new PCB out of this schematic, and this is how actually these differential inputs are directly connected to these differential outputs here of this DA converter board. So means I go with 1 volt peak to peak in here, and I was able to, I measured like 3.5 watts at the output. Of course, with significant heat produced by these two output transistors here, but that was not bad. It was well enough for more than one FT4 QSO with Spain and Norway. So that was, yeah, I think it's not bad for 3.5 watts. Of course, with Whisper, I even got further, but say talking of full QSOs, these were, say, my distance records so far with this setup here. Yeah, that's the hardware. Of course, there's also a bit of software involved. This is what I will talk about next. And of course, the software has to control not only, say, the signal processing chain, but also some peripherals. Means the software needs to control the up converter frequency. Software needs to control the amplifier enable and the transmit receive switch. Both are switched by an GPIO of this Zynq board, and there is this nice little driver from Analog Devices, this 1-bit ADC DAC driver, which just takes a GPIO and turns it into a 1-bit ADC or DAC, and then means you can directly control directly from GNU Radio. You can set GPIOs without using any extra blocks. This is very nice. This is what I used in order to to control my peripherals. The amplifier operation point, yeah, I used the stock IO digital pot driver in order to set that operation point. And the output load pass means the big one with the relays. This is controlled by an I2C port expander. I needed to write an IO driver for this because there wasn't an existing one for this particular port expander, but it was not hard to say modify an existing driver to talk to this port expander instead. That means all of the hardware parts of my SDR. Yeah, talking about software, this is then how the block design in total looks like. I don't want to go into much detail here. It's pretty straightforward. Yeah, so the peripherals are controlled via IIO blocks here. Of course, the audio data is transferred via IIO, and as well as the digital up converter frequency. But what was a bit tricky, this is something that I would like to show you because it might be of help for some of you. I had the problem that I wanted to set one variable in GNU Radio in dependency of another variable. Looks like a straightforward problem, but I didn't find an easy solution, so I had to use a workaround. Maybe some of the GNU Radio guys will tell me how this would have been more elegant, because I wanted to set my digital up converter frequency depending on the desired transmit frequency. Means I needed to quantize the frequency to the nearest integer multiple of my sampling rate, of the sampling rate on the Ethernet interface. So how did I solve this problem? I chose a variable block where I do the actual calculation. Then I have this variable monitored by a variable to message block. And if this variable changes, of course, a message is emitted. And this message is then fed into a message pair to variable block, which will then in turn set a different variable. I'm pretty sure this is not the most elegant solution ever. I'm happy to hear how you can do this differently, but it did the trick for me. So this is how why I did it like that. Yeah, feel free to tell me in the discussion afterwards how to do it in a more elegant way. I will happily change my block design then. Yeah. How do I interface to the outside world? The answer is using the zero message queue protocol, because of course I need to interface with external software, for instance WSJT-X or FLDigi. That means I need some way to talk to my GNU Radio block design, GNU Radio block set, and I chose ZMQ for that. And in order to translate from rig control cat to zero message queue, I wrote a little proxy server in Python that takes commands on the cat interface, on the rig control daemon port number, and translate it into ZMQ messages. And by doing so, I can use my GNU Radio flow graph in connection with existing ham radio software. I used a script by James Alstrom as a starting point. You can find it here on his website. It's very well explained, and you can easily extend his code in order to do the stuff you would like to see. Yeah. Yeah, and using all this, say, very complicated, delicate contraption of components, I ended up with a very complicated block design. I will just jump forward to this, how this looks like. Yeah, so it's a really combination of very different software parts and hardware parts. What's important is that, of course, the audio between the different blocks of software is exchanged via pulse audio null sinks. And while doing this, while plugging all this together, I ran into a, say, big problem using pulse audio. And this problem is the follows. The generic GNU Radio input-output blocks, they don't use pulse audio natively. They use the ALSA compatibility layer. And that means there is no guarantees on latency and the like. And in my situation, as soon as you have a packet loss on the Ethernet interface, on the interface between the IIO block and the actual transmit hardware, the two clocks start to diverge. And means you have this very, very famous two clock problem. And that means that pulse audio isn't able to get its sample delivered, and its FIFO will fill and fill and fill. And after a few minutes, I was running it, say, into 2-digit seconds of latency between these different blocks of software. And what I did to solve this was to write a native pulse audio source block. Yeah, so it wasn't that hard. There is a lot of example code out in the internet that will help you to do this. You can also find this native pulse audio source block on my GitHub. Here down there is the link. And this block really sets real-time audio. Yeah, so it requests real-time audio in order to say rather drop audio than have it buffer for up to several seconds. And this helped a lot, and this also finally got me in the situation that I was able to do FT8 and FT4, yeah, because of the latency, strict latency requirements. So that finally worked out. Another thing that I've noticed was that while WSJT-X has a native pulse audio output, it doesn't request real-time audio for some reason. I don't know why. So this is why I patched the sources of WSJT-X. You can see the patch here on the right. It's basically if you use the game profile when you open the pulse audio connection, you will basically get real-time audio. And this again helps the situation. So maybe I should upstream this patch in order to get it included in the mainline version of WSJT-X. Yeah. I just showed you this picture here. What you also see in this design here, yeah, the yellow parts are the ones that I wrote myself, and the white ones are, say, commercial off the shelf, basically. You see that I used an AirSpy for receiving, even though last year I showed you my own software-defined receiver, but to be honest, you can't beat the performance of the AirSpy, HF plus Discovery in this case. So this is why I used the setup here. I use the AirSpy for receiving in connection with GNU-Rx, and I use GNU Radio and my own design for transmitting. So this is how I get the best of two worlds. Yeah, so let me now wrap up my talk. Let's come to the conclusion. Time's running out. So yeah, building a homebrew transmit SDR. It can bring a lot of fun. Of course, it can also bring a lot of pain, but the fun is even larger after the pain is gone. So actually, you will cover a broad stretch of fields. Yeah, when you do this kind of thing, you need to do an RF design. When you do the analog RF parts, you do the PCB yourself. You have to take care of the analog parts of the DAC circuits. Then you go into the FPGA and then to the Linux world. Yeah, a lot of different, say, cogs that are, say, interacting with each other, but when it finally works out in the end, it's really satisfying to actually have your first QSO on your self-built transceiver with someone else in the world who most likely doesn't even know what piece of hardware he's communicating with. But knowing that you built all this yourself, really, it's really worth the pain on the way there. And I have to admit this, of course, building all this hardware always is much more fun than only having QSOs later. I'm this kind of ham radio amateur that really the fun is the building, not the using. So I'm also off in my head to the next project. Let's see how far I can get there. Yeah, that concludes my talk. So thank you very much for your attention. And of course, I'm now open for question in the Q&A. Thank you very much.
Yeah, so thank you very much. Henning, that was a very, very interesting talk. So it is always a good attempt, or worth trying something very funny with little pieces of hardware which you can get partly even very, very cheap. I'm looking at the clock, it's 16:01, which means that we're actually over time. And the next speaker is already on the stage. So, well, I just said we're actually a little over time, it's past 16 hours. And the problem is that all the discussion we're having now must be deducted from the speech time of your second talk. So I would suggest to allow one question. Is that okay for you?
Yeah,
Good.
sure.
Is there one question? Oh, the audience is so polite, so speed up. Okay.